Next, we will discuss a few applications that involve integration in polar coordinates. And the first one is finding arc lengths. So let's consider the following problem. Let's consider the polar curve given by this equation. And let's find the arc length on the interval from 0 to pi over 2. So one way to approach this problem is to write the equation in Cartesian form and then use the formula that we already know for finding the arc lengths in Cartesian coordinates. So how do we do this? So we can rewrite the equation as f of x, and you can check yourself that this is indeed the same equation. You can just use Desmos and plot both of them, and we can use the following formula. Integral from a to b of 1 plus f prime of x squared dx, and that will find the arc length. Now, alternatively, we can parameterize the equation and in this case, parameterize means what? So we're going to create two equations, and x will be r, which is 2 cosine theta times cosine theta. So it will be 2 cosine. I'll rewrite it as a new set of equations later. And y will be r times sine theta. So our parameterization will be x of theta equals 2 cosine squared theta, and y of theta will be sine of 2 theta. And if we can parameterize it, then we can use the following formula. So we can integrate from theta 1 to theta 2, or in general from some alpha to some beta. We're going to integrate the derivative with respect to theta squared plus derivative of y with respect to theta squared, and all that d theta. So this is something that we learned in one of the previous sections or lessons when we discuss calculus with parametric equations. So we're going to explore the second alternative, and we're going to continue this process. And what's going to happen in general? So let's see. We're going to have some integral from alpha to beta, and x theta is always r, which is a function, right? So it's r of theta times cosine theta squared, and we have r of theta. I forgot the derivative there, so we have to differentiate this and then square. So first we differentiate, then we square. So it looks scary right now, but hopefully it gets better. So let's find the derivative of those functions, those are the products, and we have to use the product rule. So we're going to have r theta. So we're going to have derivative of r times cosine theta plus r times derivative of cosine, which is negative sine. So I'm going to bring the negative to the front, and all this squared. And we're going to have plus r prime times sine theta plus r times the derivative of sine cosine theta. And this is also squared d theta. And we're going to continue the process. And we're going now to square everything. So we're going to have r prime squared, cosine theta squared, minus 2 times the product, so 2r r prime cosine theta sine theta plus r squared sine squared theta. Now it starts to look promising, because I kind of see the opportunity to apply the Pythagorean identity soon, but let's wait. This is 2 times the product and the last term squared d theta, and we're almost there. We just have to now simplify as much as we can. We have integral from alpha to beta square root, and now this 2 times the product cancels because those are identical terms with opposite signs. And now if we combine the like terms, so this term can be combined with this term, and because sine squared theta plus cosine squared theta is 1, we have nothing but r prime squared left. And same here, this combined with this, we factor out r squared, and we have sine squared plus cosine squared, which is 1, so we have r squared. So it turns out, if we continue with the second option, which was the parameterization, we would end up always with something like this. So instead of actually parameterizing and going through this process over and over, we're just going to use this formula to find the arc length of a polar curve. So let's do the same example again, but this time, instead of considering all the alternatives, we'll just do the formula. And the formula, again, for the arc length is integrate from alpha to beta. Those are your boundaries. And we're going to integrate the following expression. So in our case, what do we have? We have interval is from 0 to pi over 2. R prime is -2 sine theta. So plugging everything in, we get L is equal to integral from 0 to pi over 2 square root of -2 sine theta all squared plus 2 cosine theta all squared d theta integral from 0 to pi over 2 4 sine squared theta plus 4 cosine squared theta the theta, and we can finish it now. Factor out 4, and then according to the Pythagorean theorem, sine squared plus cosine squared of theta is equal to 1. So we're almost done here. So square root of 4 is 2, integral of 2 is 2 theta, and we evaluate it from 0 to pi over 2. So the answer is pi. So let's try another example. Let's find the arc length of r equal secant theta for these values of theta. We're going to use this formula. Again, we got this formula from considering the parameterization of the curve. So this is where we use our knowledge of parametric equations. Let's find the derivative. Derivative of secant is secant theta tangent theta. Now we evaluate this setup first, then evaluate this integral. You have to be okay with trigonometry when dealing with trigonometric functions in problems like this. Let's see. We square everything, and then let's factor out the secant squared. So we get tangent squared theta plus 1. And we have secant squared theta, and tangent squared theta plus 1 is actually another secant squared theta. So we have square root of secant to the power 4, which is the absolute value of secant squared theta, but since secant squared theta is always positive, we don't need the absolute values. And it's always defined, at least on this interval. And what's antiderivative of secant squared? It's tangent theta. So we get antiderivative is tangent, and we evaluate it between pi over 3 and pi over 4. So tangent of pi over 3 minus tangent pi over 4. Tangent of pi over 3, it's sine of pi over 3 over cosine of pi over 3. So it's root 3 over 2 over, so it looks like it's root 3 minus 1 is the answer. So it's pretty straightforward. So let's do another one. This time we're not going to integrate it by hand. We are going to just set up the integral and use technology to evaluate it. So again, the question is to find the arc length of this curve on this interval. And we're going to set up the integral. So first we're going to find r prime, which is negative 4 theta squared, and we're going to set up the integral. We can simplify it before we pull out from alpha and plug it in, but if you feel like it's too risky, then you can throw it in Wolfram Alpha as is. And here we have what? 16 over theta to the 4 plus 16 over theta squared. And I don't think this is the type of integral I do want to do by hand, so let's see what Wolfram Alpha has to say about this one. I'm going to type this in here. So we have an integral from 2 pi over 3 to 3 pi over 4, and we have this integral, so I'm going to put it in parentheses, and we put d theta, but instead of theta I'll just use letter x. So the integral will have a square root, and inside of the square root we have 16 over x to the power 4 plus 16 over x to the power 2. So let's see if it interpreted the input correctly. Is that what we have? Yeah, it looks like that's what we have. Based on this, it looks like this is something that we could have done by hand. It would have taken us maybe more than 5 minutes, but since there's a formula, we definitely would have figured this out. But let's just copy this answer over here, and we got the answer, right? So approximately the arc length is equal to 0.517. So we discussed how to find arc lengths in polar coordinate, which is one of the applications of integration in polar coordinates.